Hey, I know last week we said that we'd be working with an exponentiator and some paired transistors, but I thought, we could do that, and I could talk about millivolts and songs and how important it is to get all of this balanced, but maybe it'd be better to actually start with something that makes sound. So I've built this little oscillator circuit here, and we're going to get into that a little bit. But first, let me talk to you a little bit about the importance of this power supply. It really just saved me today. I came back down here to the shop, I turned the power on, and I wasn't getting any sound. I didn't get my tone. I just heard a little crackle from the speaker. It turned out when I had plugged the speaker back in, instead of plugging it into the output of the circuit, I had plugged it into the negative rail. And so it would have been sending 12 volts across that speaker. And if I didn't have a power supply where I could limit the current, that would have very quickly destroyed my speaker. And not that this speaker is particularly expensive, but it would definitely set me back because I wouldn't have a speaker, right? I'd have to go get a replacement part or find some other wiring way to do it in some other means. So because I had my current limited, I saved myself a trip to the shop. And today we're going to talk a bit about power and in more ways than just that. But first, let's take a look at this circuit that I built. I want to show you the schematics. Okay, so my power supply doesn't have a ground. It just has a positive and negative. So for most of these audio circuits, we need a minus voltage source, a positive voltage source, and a ground. And so what we need to do is we need to create a ground. And one way to do that is with an op amp like I've drawn it here. The circuit's actually implemented with a buffer. Maybe we'll get into that later, the difference there. But the way this works is we have a voltage divider from 12 positive to minus. These two resistors are the same, so in between it's going to be exactly halfway between those. So if I put 24 volts on my power supply, I'm just going to call this side minus 12 and that side plus 12. My power supply is just supplying 24 volts across here, and in between will be halfway in between, and so if we call this minus 12 and that 12 plus 12, then this will be 0 volts here. Then we have this op amp that we talked about last time. It has negative feedback. This is a tiny little resistor. We can almost pretend that it just doesn't exist. If this is ever too high, right, if something is dumping positive voltage into the ground, we have some current flowing in the conventionally direction towards ground, right, it's going to bring this voltage up, and so this op amp is going to try to drive it down, because if this is higher than that, then we're going to drive negative voltage, right? And the symmetrical thing happens the other way around. So this is how we can construct a ground with high impedance, so that when we're dumping current in or pulling current out of ground, either way, this op amp is going to keep that ground at 0. Okay. So let's come over here to the actual oscillator circuit itself. Bear with me. This is a little bit more complicated, but it's really cool. This is also called a multivibrator, because what will happen is this op amp will be flipping between all the way to 12 volts and all the way to negative volts. The op amp can't go beyond its rails. Some op amps will go all the way to the rails, but a lot of them won't go quite all the way. But anyway, let's look at what's happening here. We have a capacitor over here, and so let's just imagine that starts, not charged, and so we have 0 volts here. Then we have this voltage divider going down to the negative rail, and so we have some negative voltage here hooked up to this plus, right? And so if this is negative and this is 0, the op amp is going to say, "Oh man, we got to get negative," and so it's going to shove negative 12 volts, out this. It's going to keep on pushing that down, and so we have a negative voltage coming in here, and so then this is highly negative, but this capacitor has 0 on it, so this current's not going to be able to go in there. It's pushing negative volts here. It can't go. It's conventionally the current. We can think of the current is going this way. It's pulling it through this resistor because it has a negative voltage here, and this started at 0. So what'll happen is it'll pull current up from the ground through the capacitor, and the capacitor will charge. And that capacitor will just keep on charging until this gets high enough. And when that gets high enough to exceed this threshold that's created by this voltage divider, then it's going to flip around, and it's going to push positive here. Right? and then suddenly this is high, right? And so this target thing that we're trying to get to is no longer a negative voltage, it's a positive voltage. So now it'll flip back around, and we'll get a positive here, and it'll drain the charge across this capacitor. Okay, so this here basically sets up a voltage divider that determines what bounds, where the flipping point is for this capacitor, and this here is what we call the timing resistor. So the rate at which this charges is determined by this resistor here, because the current is coming this way or it's going that way, either charging or draining this capacitor. And so that is what determines the frequency of this oscillator. So right now I have wired up like this, and this one that I've labeled as 10K here is actually a potentiometer on the board, and I'll show you that in a second. Okay, so then let's skip over this for now. This is an amplifier. I don't think I'll talk about how exactly this amplifier works, but we'll come back to it in a second. It allows us to amplify that signal, and so that I can adjust it with this variable resistor. And then this 8 ohms out here, this is my speaker. And this can go from -12 to 12, right? And so I've set this up here, 68 and 8, so that the voltage divider won't send more current or more voltage across my speaker than it can handle. Okay, well, enough about the circuits. Let's take a look at the implementation. Okay, great. I've got this hooked up. You can hear it's making that oscillator sound. This is that capacitor that we were talking about before. And if I take my scope probe and I measure the voltage across that capacitor, we see this really cool shark tooth pattern. As the capacitor charges, it reaches some threshold, and then it discharges through that timing resistor. It charges and discharges. And of course, this is happening thousands of times per second, or at least hundreds of times. Sounds kind of low. And this resistor here is the potentiometer that controls the volume. And so I've set it up so this should make it louder. And it does make it louder, but it's also changing the pitch. Why is it changing the pitch? Why is it changing the pitch? Okay, back here at the schematic. This is the way I wired it up initially, and I thought it would work, but it doesn't. There's a problem. I have my capacitor here that I measure my voltage across, and the first way I wired it is I came straight from this cap to this amplifier circuit. And what happens is that this capacitor, in addition to being charged or drained through this resistor here, it also has these resistors here and this voltage source here. And so we have some additional current going this way. And so depending on where I put this potentiometer, not only is it going to change the amount of amplification on this circuit, but it's also going to drain or source current to the capacitor, which is going to change the frequency. So what we need is a buffer in between. And so now we have this cap coming to this little buffer circuit that looks just like the one we saw before with the voltage divider to create that ground. And so it's just exactly following whatever's there. And now we have high impedance here, meaning that no current is going to flow from this capacitor into this op amp. If it's an ideal op amp, zero current flows in there. In practice, it's almost like a mega ohm resistor or something on that order of magnitude. And then its output is what we put into our amplifier. So let's fix the circuit and see how that sounds. Okay, so now I have the circuit wired up the right way so that it's going through this additional op amp here as a buffer. And so now when I turn it up, it gets louder and the pitch doesn't change. But do you hear how the quality of the sound changes? Down here it's kind of this pretty pure triangle, and then listen. As it gets louder, it gets more distorted. Let's take a look at what that's like on the scope here. So we should be able to just grab the output, which will be right here. We need to increase the resolution here. As I bring this up, My oscilloscope is a little cheap and it's having trouble triggering on that. But you see, as I bring it up higher, I hope you can see that. You see how the top of that peak is getting rounded off a bit? It has a little inflection point. Let's see if I can pause it here. There we go. You see how it comes up and then goes over. And if I bring it down a little bit, it's that perfect sawtooth wave. So what's happening here? Let's see, on our scale, we're only looking at 200 millivolts per division, right? So this is a really low signal. It's not even getting anywhere close to the 12 volt rails. So why is it that it's distorting? Well, it's because this little op amp here can't push that much current. It can't drive the speaker, which is a very low resistance, with 12 volts, because it can only push about 25 milliamps. So again, there we go. The power that the circuit can handle is changing the acoustics. And now, I really like the sound that has. It's a pretty cool type of saturation. And so I want to find a way to capture that overdriven LM741 sound. And one nice thing about the LM741 is that it can drive to short circuit indefinitely. So it has some protection in there that it's going to be okay. One thing it doesn't have, though, is heat shutoff. And so I do have to be a little bit careful about how much power is being dissipated by that LM741, but we can definitely get it to a state where it's overdriving in order to produce that kind of interesting saturation. So for next week, I think what I'd like to do, don't hold me to it, but is replace this resistor, this potentiometer that I have here for the pitch. I guess I didn't show that to you, but I can turn this potentiometer to change the sound, change the pitch. Yeah, let's listen to that. So as I turn it up, it gets higher, right? And as I turn it down, it gets lower. But down here at the bottom, I have to turn it a lot to get it to change even a whole step or so, right? And up here at the top, right, it has to change. I turn it a little bit, and it very quickly gets higher. And that is the exponentiation thing that we were talking about before. But before we get there, what we have to do is we have to get this to be voltage controlled instead of a potentiometer. You don't want to be turning a pot with a screwdriver in order to play music. You want to have a voltage source going in there from a keyboard, or a control voltage from some modular gear, sequencer, whatever, to determine the pitch. So I think that'll be the next piece. If you have ideas about how you'd like to see that done, or maybe ways you've done it before, because there are a lot of design options there, let me know in the comments, and I'm going to do some research and we'll see what we find. Okay, thanks for joining me. Bye.